Hi everyone, my name is Dhruv Karthik, and today we're going to look at reactive methods for planning. They're an amazing class of methods that just work for so many racing strategies. So this is a quick example of a reactive method in action. See how it's easily able to rapidly race around the track and weave through all of these densely populated obstacles. This is the car. And yeah, this is it in real life. Notice how it's able to accomplish a similar thing. So the question is, how do we get to that level of performance without a map? And follow the gap is an algorithm that attempts to answer this question naively. And in order to motivate this algorithm, we're going to take a look at a LiDAR scan in the same way that Ross gives it to us. So if you recall, Ross gives us this array, a 1D array of ranges, where each sort of range refers to how far the closest obstacle was in that range. And the question is, where should the car go? Right? An obvious choice would be just go toward the furthest point away from us. And the furthest distance might be wrong. And why is that? You might want to pause here and figure out why that is. Well, the reason is because as it approaches this inf, it's going to get caught up by these two threes to the left and right of it. And yeah, in doing so, it's going to sort of, the ray passes through, but the car won't because it's too big. It's just going to grab itself on these threes. And so that motivates the follow the gap algorithm. Of course, this sort of getting it stuck between two gaps isn't the only issue with this, furthest distance following algorithm. It's just one of the most obvious ones. So that motivates the follow the gap algorithm. So gap is considered a series of at least n consecutive hits that pass some distance threshold t. Right. So if n is equal to 3 and t is equal to 5, you should probably pause here and figure out what the gaps are. But the first gap is this sort of gap of length 4. All of these are greater than 5, and we have at least 3 consecutive sort of hits. And then the second gap is these 3. We have an inf, an 8, and a 5, and then we have 3 consecutive hits. And sort of what this algorithm does is that it simply picks the largest gap and steers towards its midpoint. So, and there's a reason that this naive follow the gap does not work. So this is an example of our scene, right? In orange, we have our LiDAR hit points. In blue, we have our distance threshold. And our follow the gap algorithm results in this being considered the largest gap because it's the largest number of, say we have over here, 1, 2, 3, 4 consecutive points that are outside of this distance threshold t. So, I mean, what it's going to do then is that it's going to steer toward the midpoint of this gap because this is the largest gap. And in doing so, it crashes into this left obstacle. So it's a very similar idea, but it's more subtle in this scenario. And this idea of seeking out the largest gap actually works perfectly fine for holonomic robots like turtlebots. And the good thing about these robots is that they can turn 360 degrees in place. And it also works for non-holonomic robots like the F110 or other autonomous race cars that are in environments with sparse obstacles. However, it doesn't actively optimize for safety, and it doesn't consider the car's dimensions. And finally, it's also very difficult to decide this distance threshold t. Like this often changes a lot based on how densely populated or how sparsely populated your map is, and you can't change this threshold in between arrays. So this is a quick example of the UNC follow the gap algorithm, and this actually won the F110 Grand Prix.
That we were just about unsafe, but still safe. And you'll see one of the videos where we decided we weren't going to go quite that fast anymore. So I'm going to give you a really high-level idea of what we did. Our general mantra was find the farthest distance and go there. But as you can imagine, that's not always going to work. You might try to go the furthest distance and then you're going to hit a wall. So instead, to handle that, what we did is we took the LiDAR readings and we looked for disparities. This would be anywhere where there's a wall blocking a reading, so you have consecutive angles of the LiDAR giving you very different numbers. And this indicates that there must be something blocked. So in this case, we have a disparity where we see maybe 2.2 meters and then 4.8 meters. Now we took that to mean maybe that is turning a corner and that's the path we want to take. If there's no disparity, that's because you have a smooth wall. That was our mentality for this. So, that's a good approach, but it's not quite as much as you need to consider, because if you just consider the LiDAR readings, as we've seen, you could hit a wall. So it was important to us to expand out the wall so that we're not going to hit it. Did you have a question?
Yeah, at what rate were you obtaining the readings?
I believe it's at 40 hertz.
40 hertz.
So our
wow.
goal was
Okay.
to stay below 25 milliseconds, and I think we kept it around 8. Thank you. So what we did is we took the disparities and we effectively moved them out from the wall to kind of extend the range of the wall so that we would only pass through safe positions. So this might mean that you figure out the number of angles that correspond at that distance to the width of the car, and we're going to extend a circle and then cut off those LiDAR readings. And we're effectively working with some virtual LiDAR readings at this point. So based on those virtual readings, we have my very shakily drawn image that indicates the path that we actually are going to treat as the free space to move around. And now we don't have to worry about the size of the car. Using that, we figure out the furthest distance, and that's the direction we travel. So we make local decisions, and we are pretty confident that this very closely approximates the global optimal shortest path. A couple other details: it is greedy, so we might not be making always the best decisions, but we're very close. We choose our speed based on distance, and we have a piecewise linear function to determine the speed based on the furthest distance that we see. And again, it's a very, very quick processing. We made it very, one of our goals was to use every LiDAR reading and process fast enough.
Here we're going to describe the F110 follow the gap, which is a variation of this UNC follow the gap, which the idea is at every time step we should cleverly avoid the nearest obstacle. So let's take our scene again. So step 1 is to find the nearest LiDAR point and put the safety bubble around it of radius RB. So already notice the difference. Now we're not looking optimistically at the furthest LiDAR point away from us, but instead we're looking pessimistically at the closest LiDAR point to us, which represents the closest obstacle that we could hit. So we're going to put a safety bubble RB around that. And yeah, notice how it's the closest hit point in this array. In step 2, we're going to set all the points inside this bubble to distance 0. So we're just going to flatten them out. That ends up being these points. All non-zero points are considered free space. So all other directions represented by this LiDAR array are considered valid steering directions. Next, we find the maximum length sequence of consecutive non-zeros among the free space points, which is the max gap. So the maximum length sequence of consecutive non-zeros in this sort of hit point array happens to be, well, there's 2 sequences of non-zeros. There's these 2 or these 3, and there's this whole chunk. And obviously the right side is the max gap. Next, we find the best point among this maximum length sequence. And so far, all that we've been doing is go toward the midpoint, and a naive improvement over that is to choose the furthest point in free space among this free space sort of max gap area, and then set your steering angle toward it. And then we go toward this furthest point. But the issue with this is that drastically changing your speed results in you losing velocity very quickly. And the intuition for a better idea is, if you're 3 to 4 meters away from the closest obstacle, should you immediately make a sharp turn to avoid it? Probably not, because it's, relatively far away. What you probably want to do is curve into the obstacle or curve away from the obstacle over that period of 3 to 4 meters. So the key takeaways from this algorithm are that, first of all, it's immediately more pessimistic than the previous algorithms. Previous algorithms said optimistically find the largest gap and drive toward it. Unlike that, what we're doing over here is actually something different. We're encoding the car's dimensions within this sort of safety bubble. A good radius for the safety bubble actually is just over the width of the car. And since we're encoding that information, we're explicitly telling the algorithm to avoid the closest obstacle, which represented by this point, by a certain margin. We're trying to clear it by a certain margin. And naturally, instead of having this fixed safety threshold T value, what we're doing is that as the car approaches this obstacle over time, more of its LiDAR points are going to be concentrated around this obstacle. And this sort of safety threshold will correspondingly get bigger. So already we're seeing that we're dynamically varying the size of the safety bubble. Although the radius stays constant in world coordinates, as the car gets closer, that world coordinate representation will take up way more LiDAR points in general. So it's going to occupy more LiDAR points. Um, so this bubble keeps changing in terms of the car's perspective and size. So we don't have to have a fixed safety threshold T. And yeah, finally, it's turns out to be a much faster algorithm.